University of Toronto. I've been responsible for North American market since 1993 with Geonics. My duties have included instrument training, technical software support, as well as general sales and marketing. Over the last 29 years, I've been a regular trainer at a lot of different geophysical field schools. I've conducted training sessions and workshops all around the world, covering a wide range of applications, including mining, groundwater exploration, environmental, archaeological, of course, agriculture, as well as military. Some of the clients have included, of course, the USDA, DOD, EPA, DND Canada, DCC, the U.S. Army Corps of Engineers, Navy, Army, Air Force, FBI, a lot of other different police forces, some forensic units, quite a wide range. Anyway, with that, what I'm going to do, of course, is shut down my camera and we'll start the presentation. So let's give me a second here. All right. So I'd like to begin by, of course, thanking Chad Ferguson and the NRCS technology team for inviting me to speak today. When I first came across the tech team group and the website, I was actually struck by a couple of statements that I had read. First was that your team was established in order to bridge the gap between historical tools like the auger and shovel and tools of the 21st century, and it emphasized participation as the primary requirement. It's always a good thing. The second was that EM sensors were identified as one of those 21st century newer approaches to soil resource inventory that should have people exposed to it, and that the focus team would help facilitate that. Well, today I hope to play my small part in advancing all your knowledge just a bit more when it comes to making use of EM sensors and, of course, measuring soil conductivity. Let's first review what will be covered in today's talk. We'll start with a quick introduction and history, followed by a review of the EM induction theory, how EM sensors, also known as ground or soil conductivity meters, work. We'll then cover depth of detection and what can be measured with EM, including introducing those not so familiar with the concept of also using magnetic susceptibility with EM sensors, not just conductivity. We'll go into a deeper discussion that follows, covering all the factors that affect soil's electrical conductivity, such as moisture, water content, texture, salinity, organic matter, pH, the effect of clay, and then case histories actually showing how conductivity is used to map the changes in each of these factors. We'll also have examples of some variable rate applications, yield maps, management zones, and how EM conductivity is used with that. So hopefully by the end of the talk, you'll all have a much better understanding of how EM actually helps increase overall productivity and health of agricultural lands. So to start, I'd like to briefly review the basic principles behind the operation of our EM instruments. And so there's two general cases of EM instruments, two general classes of EM instruments. There's frequency domain and time domain. Time domain instruments produce a short, low energy electromagnetic pulse from a transmitter coil, while a receiver coil measures the decaying signal induced in the ground as a function of time. The rate of decay is then related to the electrical conductivity of the subsurface materials. This technology tends to be used more for mineral exploration because it's more advantageous to go very deep with that type of equipment. The frequency domain method, on the other hand, uses inductive properties of a fixed frequency, continuous primary EM field by measuring the amplitude and phase of the induced EM field, which is directly proportional to the conductivity of the material through which the field passes. In this case, with our EM sensors, that material happens to be soil, and soil is a pretty good conductor. And we'll be using it to our advantage and explaining in some of the basic theory behind that. Of course, the presentation is going to focus mostly with examples based on Geonics EM instruments. Just before we get into the theory a bit, just a quick brief history on the systems. These are just some pictures of some of the earlier manufactured systems patented by Geonics, which were the first to patent the EM technology. We've been building them since 1962, which is how long we've been around. And we basically include every pretty wide-ranging type of instrument. We made both small and large ground-based airplane helicopter mounted systems for both mineral and groundwater exploration, as well as for environmental engineering and site characterization. This is actually the very first instrument manufactured by Geonics, and it happened to be called the EM15, 1963. The reason for the naming, out of interest here, the very first instrument used an operating frequency of 15 kilohertz, and we'll get into that deeper into the talk. But because that was the operating frequency, we decided to name the first one an EM15. Believe it or not, all we did after that was every time an instrument made it to market, that actually made it to market, not just introduced by the R&D department, we added one digit to it. So there's actually been that many. When you hear EM61 or something, that's how many instruments have actually been developed that made it to market. So it's kind of a cool thing to bring up. And another interesting fact here, you can see that the coincidence between, I find it hilarious, the very first instrument we ever developed looks almost, has quite a resemblance to the widely used EM38, more modern tool, which is used across, of course, very popular in agricultural applications. And what does it look like? The most popular one that is used for across your departments and for ag purposes. Basically, very small tool, about 1 meter in length. Another interesting fact on this instrument is a fact that we recently had the very first one developed, included and added to the Canadian Agricultural Museum. Just a list of, as I was talking about all the different numbers and names, just a quick breakdown of some of the nomenclature of our instruments. But now we'll get into the fun stuff. So let's actually review, and what I hope most of you actually came for was the applications and a better understanding how things are working with EM. So in terms of the physical principles of the measurement and operation with these frequency domain systems, those that are really interested in a more in-depth analysis, you can actually look up the listed books by Grant and West, Telford and Beck. I've just listed a few here. If you want a more user-friendly read, layman's terms, not too heavy on the math, then you go to our website, and there's a couple of technical notes, TN 5 and 6, which you might be familiar with, that pretty much give you the whole story in much more detail, but again, still in layman's terms. So to start with, let's point out that the theoretical basis of operation for all EM instruments, they're all governed by two very important laws of physics. They're known as Ampe's law and Faraday's law, which together form the basis of the principles of electromagnetic induction. The phenomenon that we describe as Ampe's law, it's illustrated in this slide as both an animation and as a mathematical equation. It simply states that any wire where an electric current is flowing is surrounded by an invisible force field called a magnetic field. In all Geonics instruments, we take advantage of this phenomenon by using a transmitter and receiver coils. This slide shows that the dipolar magnetic field looks like when we send current into our transmitter loops. Keep in mind that the strength of the magnetic field is directly proportional to the current that flows through the wire or the coil, and it's much smaller as you move away. Now, Faraday's law, on the other hand, states that moving a wire into a magnetic field generates an electric current into that wire. And this is illustrated here as we observe the needle deflection of the voltmeter, which measures the induced force or current generated into the coil as the magnet passes through it. So Geonics takes advantage of this by using an AC current with our transmitter coils that grows and shrinks the EM fields, inducing current in a nearby conductor, which of course, for our purposes, is the soil. Now, let's take a look at both Ampe's law and Faraday's law and describe how they are used specific to our ground conductivity meters. In the following slide, the TX represents a transmitter coil within our instruments where we pass the AC current that sets up the primary magnetic field, which is labeled H sub P. And it causes what we call eddy currents in the soil. These currents create a secondary EM field labeled H sub S that has a characteristic intensity and time variation with respect to the primary field that is directly related to the electrical conductivity of the soil. A nearby receiver coil labeled RX is used to measure the in-phase in parts per thousand of the transmitted field strength, as well as the quadrature out-of-phase component of the resultant EM field. And it derives the apparent electrical conductivity from the quadrature component for the soil directly below the instrument. In other words, the resultant field measured at the receiver coil, it's a combination of the primary and secondary fields, which differ in primary field in both phase and amplitude, just as illustrated in the graph. After compensating for the primary field in the electronics by using positions and orientations of the coils, we can obtain both the magnitude and relative phase of the secondary field. So the ratio of the secondary to primary is what we ultimately calculate and output as the apparent soil's conductivity in units of millisiemens per meter. As well, Geonics frequency domain instruments can also measure, of course, the in-phase component, which is measured in parts per thousand, as I mentioned. This measurement is also known as the magnetic susceptibility measurement. And as will be shown later, basically it's an underused measurement, which I'm trying to inform people more of across all fields. So although the depth of investigation with EMI instruments is controlled primarily by the spacing between the transmitter and receiver coils, it's also influenced by the orientation and operating frequency of the instrument. These factors basically all contribute to the development of a wide variety of soil conductivity and metal detection instruments. And this slide, just a quick example of some of the more commonly used systems with the various specifications. And obviously the distance that coils and transmitters are going to be affects what the instrument's going to look like ultimately. They all work the same way. In order to manufacture these usable systems, we also have to select each of these parameters in such a way that we allow the internal calculations to be simplified by making sure that linear relationships exist between what we call the mutual coupling ratio, which is that ratio of the secondary to primary magnetic field, and the apparent electrical conductivity. In most of the technical literature, this concept is referred to as the induction number, which you'll hear sometimes. And simply stated, Geonics instruments make sure this number is much less than 1. Mathematically stated, you can see that the coil separation S divided by the skin depth must be less than 1. You can also observe that from the graphs, the general response is how all the curves are linear at the induction numbers of less than 1. Now, although the operating frequency of each Geonics instrument is fixed, each varies inversely with the coil separation to keep what is called the induction number less than 1 for most common ranges of soils, as you can see in the chart. This then allows for internal calculations, like I said, to be simplified, which makes it these linear relationships exist between the secondary and primary field and the apparent electrical conductivity in a half space for soils below the instrument. The fixed operating frequency and coil separation are what allow us to remain stable and minimize the drift of these instruments, which is another critical thing. It's just showing the conversion factor again. The chart, we're pretty familiar with this. So most EM instruments were introduced to the market with a specific depth in mind, but they all have a major built-in advantage when it comes to depth of investigation. Since our conductivity instruments are coplanar loop systems, we can take advantage of the geometric configuration of the coils that allows each instrument to be used in two dipole modes. I'm sure you've heard of the terms, but the vertical dipole mode is when the coils lay horizontal to the ground and generate a vertical EM field. The other is called horizontal dipole mode, where the coils are vertical but produce a horizontal field. The red graph shows the general response curve for any vertical dipole mode, while the blue shows the response for a horizontal dipole mode setup. We define the approximate depth of investigation to be the area under each of the integration of the material to the point at which about 75% of the subsurface soil response occurs. So it's basically a depth weighted average below those curves. For the V mode or vertical dipole mode, it's clear that it's about 1.5 for depth, and for horizontal dipole mode, you see that it's 3/4 or 0.75. So as a result, we can use these factors basically to approximate the depth of investigation in each mode for any of our systems. And we have the examples here of the two instruments, EM31 and EM34. In this slide, it's a schematic of the positions of the coils in vertical dipole mode for, and the more popular EM38. Whereas here we have the position of the EM38 in the vertical dipole mode. Oh, sorry, let me go back here. This is the vertical dipole mode, right? The coils are horizontal, but the field is a vertical dipole mode field there. So when I switch back and forth, the coils are vertical, but we always refer to the horizontal dipole mode of the instrument. So this is with the instrument in horizontal dipole mode. And you could see the depths are quite different between the two, right? This is just a chart with a quick breakdown of pretty much some of the more common instruments and how the different depths of detection with the varying frequencies. Here I highlight two of the most appropriate models for shallow agricultural applications, which include our current models, the EM38 Mark II and -4s. Some of the older models. And here we see our current model in use. The picture to the far right shows a typical example of the actual calibration or zeroing procedure, which is required by all EM sensors prior to their use. It generally only takes a couple of seconds, maybe 30 seconds once you've got things going and understand it. And you actually now, it's even less than that because a lot of the calibration procedure can be done. You have a choice of either doing it manually or in an automatic mode. You can literally press a button in the software and it'll take care of the calibration for you. Something a lot of people probably are not aware of, but yes, it does exist. One of the massive benefits of measuring soil EC with EM sensors is, of course, the fact that they're so lightweight, excuse me, require low battery power and basically no soil contact. These are all factors that allow these sensors to be towed behind vehicles by non-metal sleds or trailers. And here's, of course, a few examples. In the next slides, I show a couple more examples. As we move along, and the one common thing you see throughout all of these, of course, is the use of plastics and wood, basically non-metallic in nature. And here, this is actually a lot of people don't realize we finally decided to build. For the longest time, we would always say, well, if you're going to tow the instrument, you have to build your own trailer or sled. But we actually offer an option for people now. So there you go. And here's nice system that was put together by the USDA ARS Salinity Labs. They call this the salt sniffer. I love this picture, and I'm actually going to get into more of a description of that in the salinity applications later on. This is the newest of our systems called the M38-4. This basically includes additional coils, which, as you now know, provide additional depth information. So more coils in a system help provide more detail to depth. This is just a more, since people are familiar with the EM38 Mark II, you can see a comparison between the two, the EM38-4 with the extra set of coils. And by having those extra set of coils, now what you have available is creating maps at different slices of the soil, and of course obtaining more detailed information. And we of course have inverse modeling software that will allow the user to make even greater use of this. As you can see, here's another example. This one is a specific example to a winery called the Roche Winery out west in BC, sorry, in western BC. And I'm not going to really go into detail about that application, just to show you that it can be done. So now that we've discussed how the EM sensors operate and the importance of the depth of investigation, let's look at the factors that affect soil conductivity, which ultimately, of course, control the response we measure with each system and allow us to use them in a wider variety of applications. So in general, we know conductivity is electrolytic and takes place through the moisture-filled pores and passages which are contained within the insulating matrix. Some of the other factors affecting conductivity of the soils include porosity, shape, size, the extent of the pores are filled by water, so moisture, the concentration of dissolved electrolytes, which basically is salinity, temperature, the presence, the amount of clay, any other conductive minerals involved in the soil, like magnetite, hematite. Here's just those factors just discussed listed here. And I'm now going to introduce each in more detail in the upcoming slides, as well as some case histories. So first, let's look at soil water content. So studies find that, or have found over the decades, of course, soil water content is the single most important of all the factors known to influence EC, since the current flow within the soil, it mainly depends on water content. As a result of the charge displacement from the water molecules, water flowing down the soil creates a pathway for electric current flow. Sometimes water movement removes soluble chemical components and suspended colloids through a recharge process, while other times they're just added through a discharge process. The map scale on the right shows red, the lowest conductivity, which maps similar zones of water content, lows, measured by lab analysis, which are also red on the left side. So we start to see some reflective comparisons between conductivity and physical data. In this example, I note the regions of high moisture content measured with a neutron probe, which corresponds with regions of high conductivity mapped with an EM38. Also important to note that the temporal difference between spring and fall response with the highest moisture content observed in the spring. This is data from a barley field showing lowest conductivity readings mapped. The purple areas correspond to zones of highest yield in green. This is data that compares water content to EC, and we see highest conductivity readings mapped in red areas correspond to the zones of highest water content in blue. Next, we'll look at how soil salinity affects soil conductivity readings made by EM sensors. Salinity of a soil is caused by the accumulation of salts and is quantified in the laboratory as electrical conductivity, EC, using saturated paste extraction. The soil water solution extracted under suction from the saturated soil paste contains several electrolytes or salts, and under wet soil conditions, they dissolve and increase the ability of a soil to conduct an electric current. The higher the concentration of the dissolved salts, of course, the higher the electrical conductivity of the soil solution. The apparent EC measured by an EM sensor is equivalent to EC-based extract and only requires a simple conversion of values. So therefore, EM sensors EC maps provide a pretty quick, convenient, efficient method for mapping the broader wide-scale variations across fields without having to wait for individual lab results. In 2000, the NRCS labs in Riverside, California collaborated to develop a method to convert EM conductivity to salinity through a software program which is still in use today called ESAP. In this picture, we see one of the primary developers, Scott Lesh, who I met on a few occasions with one of our old original EM38 dual dipole systems. The concept of developing mobilized equipment to assess salinity across big areas was actually led by James Rhodes, former director of Riverside Labs. The image shows that the salt sniffer I showed previously, and you can see it here again. Officially known as the salt sniffer platform. It's kind of funny, which basically used a 38 conductivity meter carried in the tail by sled, and then a drill rig attached to the front. In this example, we have for a cotton field in basically the Yellow River Delta of China, comparing a salinity map on the left, which was made using direct samples and lab analysis, and on the right, basically using an EM31 conductivity system, and it's an EM31 conductivity map showing the same anomalies, as you can see pretty clearly through the blue areas, the high conductivity areas, which correspond to the soil salinity. Similarly, in this example of yield in a salt-impacted Australian field, and you'll note a lot of examples from Australia when it comes to salinity, because of course they have a salinity issue. So anyway, this field, we can see the higher areas of conductivity, which also relate to the lowest yield. So next we'll get into soil texture in general, which basically is the primary contributor to soil EC in non-saline fields. The soil texture is proportion basically of the various particle sizes within the soil. Each particle size has a range of electrical charge that basically results in the particle surface holding the ions. So clay particles have a larger surface area, and they can retain soil water and dissolve solids. Therefore, they are associated with higher electrical conductivity. On the other hand, silt and sand particles have much lower electrical conductivity. And this example of a claypan soil from a very well-studied research plot, because I know a lot of people have seen this a million times, from Centralia, Missouri. The anomaly displayed clearly shows how the depth to topsoil measured by direct methods, seen on the left, compared exceptionally well to the conductivity map on the right. Again, this becomes useful in allowing the field to be completely mapped at a higher resolution and then inverting the conductivity values to a depth which cover the entire site instead of having to rely on the minimal direct observations by auger or trenching and then extrapolating. So the EM sensor data is a much more efficient way of mapping these larger areas. And from earlier data, also collected from the same field in Missouri, we see James Doolittle here. This was his data, measuring the depth of claypan in very intensively in the site. He did it with a hand auger, and then compared it to the EM soil conductivity collected continuously, in this case, along a 180-meter test line. And you can see how the profile, and I indicate with the red arrow, there's you can see the specific areas where as the conductivity dips down, the claypan is the depth increases as a conductivity. Soil pH, which is of course another important factor that can be reflected from conductivity. So the pH measured of a soil can be considered a chemical constraint, similar to acidity and salinity. Higher pH can have a serious effect, obviously, on root development. So high pH values alter nutrient availability. And some of the more recent work is suggesting it could, of course, increase toxicity risk to some of the crops. In this data set from a farm in 2007, we have a pH map on the left, which shows similar zones of conductivity. The higher pH zones correlate with the higher conductivity zones, with the red being the lowest, blue being the highest. Here we have the same fields now showing yield maps of the same. It shows zones of red being the lowest yields, which correspond to blue zones of the highest pH mapped with conductivity in the previous map. And now we'll discuss compaction. Compaction is a physical constraint to the soil. The physical constraints appear where basically the density of the soil increases. So the increase in density with the depth is common in a lot of soils, and it could be a result from natural variations in soil texture, clay content, or it could be induced by compaction with machinery or machinery traffic or humans or people or whatever it may be. As the pathways within the soil matrix are smaller, the electrons can move much easier, generating a much stronger electrical current and therefore electrical conductivity. Research field experiments were conducted on a 16 by 20 meter plot here from an educational farm on the College of Food and Agricultural Sciences, King Saud University in Riyadh, Saudi Arabia, where they showed the relationship between soil compaction and moisture content. This is a single test line which clearly shows how conductivity increases with compaction. We see 3 lines of data with the sensor carried at 3 different heights. The solid line was done with the sensor on the ground, showing the highest overall readings, although regardless of the height, conductivity clearly always increases with compaction. Here I show a couple of conductivity maps which clearly identify where most foot traffic occurs within a sports field using compaction as a source. This, of course, can help grounds crews. This is a quick method. Doing an EM survey helps ground crews become much more efficient at establishing a better watering and maintenance program. And then I have there's several examples, which I did not include due to time limitations, with horse track racing. We have golf course management applications where very similar, good examples of compaction. In this particular study conducted by the University of Ghent in Belgium, the 38 sensor was evaluated as a novel way to possibly map and model thickness of compacted soil layer in a rice paddy field in Bangladesh. The modeled conductivity measurements along section AB correlated with the thickening of the compacted layer, as you can see, which confirmed with penetration resistance measurements. So the EC maps can clearly be a faster way of doing things. The high density EM conductivity measured, coupled with the limited direct observations, basically allowed excellent mapping of the variability in the compacted layer in this particular case. Another novel growing application is certainly the use of soil conductivity for soil organic carbon mapping as a proxy. This is just an example from a paper. We see how well the EC maps correlate to SOC distribution, showing the potential use EC as a source. So up to this point, we've only discussed making use of the conductivity values measured by EM sensors. But as I explained in the operating principles of the system, a very common overlooked property that is measured automatically on every system is magnetic susceptibility of the soil. Historically, this measurement made through the in-phase response has been neglected, even though it can provide much valuable information about hydromorphic soils in particular, as I'll show in the following examples. So in order to be used as an agricultural land, hydric soils often require artificial drainage. So the type of soil drainage has a direct effect on plant development. Hydromorphic characteristics are often used as a criteria for determining the soil drainage classes. So observing and analyzing soil wetness, morphology, color, they're all commonly used assessments for these drainage classes. So evaluating these features can be an effective in determining soil drainage classes. However, this is also very time consuming, costly, and subjective because it requires in-field investigation and clarification of soil profiles. In particular, anaerobic and intensely reducing conditions found in hydric soils have been found to enhance the dissolution of highly magnetic minerals such as magnetite. Therefore, the magnetic susceptibility values are naturally very low in hydric and poorly drained or glade soils. The data on this slide was collected for a project by the University of Guelph, which I was involved with actually myself. It shows a positive relationship between the magnetic susceptibility values measured in the lab and the 38 sensor. Furthermore, according to the findings of both EMI and lab measurements, the susceptibility values in the well-drained profile are higher than that of a poorly drained profile. These are significant findings because not only can EMI measurements taken above the soil surface be used to understand the topsoil magnetic susceptibility variations with depth, but they can also be used to distinguish between high and low magnetic susceptibility zones in order to determine drainage on a wider application. So in the same field in this project by the University of Guelph, excuse me, we collected data for an entire area. You see a satellite image of the area top right. The magnetic susceptibility maps show lower magnetic susceptibility in the depressional area, which is poorly drained, and higher magnetic susceptibility in the uphill. The EC data shows soils in the depressional area have much more water content than upper levels uphill, and therefore this area shows higher EC. Together, they go hand in hand, a little bit of different information. With this added information, hopefully, I hope you'll all explore the use of magnetic susceptibility, just with the simple introduction, as a potential source of more information for classifying drainage within a field, not just using soil conductivity. Finally, I want to introduce one of the more common general uses of EM sensors, which is to delineate management zones. Zone mapping, which is a farming concept used in spatial soil studies to account for the existing soil property variations. The concept attempts to identify sampling locations through the EC map and then analyze each location based on the sampling plan in order to characterize how soil properties affect crop yield and quality and how they're distributed within the soil. This gives a farmer an idea of what treatment to apply, at what rate, and at which location the management is needed most, based on the spatial pattern of the georeference data collected, instead of assuming the treatment over the entire field, which ends up costing way more. So the following example showcases a technique developed by the Natural Resource South Australian Murray-Darling Basin. SAMDB, I guess, is their for short. This was in 2015, which uses EM38 as the basis of generating the VR maps. So the conductivity maps are used to target 5 key soil testing areas to basically then ground truth the map information. As you can see here, just quickly with the arrows, the deep soil testing is then done at 4 depths to 80 centimeters and analyzed for texture, fertility, moisture content, and other subsoil constraints. The data is then used to convert the 38 map into a zone map to be used as a control for either the application of variable seeding or fertilizer directly displayed on the tractor's tablet. So one very novel approach. Now, similarly, we have a similar example for a vineyard where the zone map for management of the field was based primarily on the EC data, which was correlated to various other nutrients also mapped. Now, in this is my final example, and it's of an apple orchard showing how well the higher productive regions correspond to the initially mapped lower conductivity or blue zones. You can you can see how clearly the EM can certainly be an invaluable tool for increasing productivity. And it's clear as day in this example. So in conclusion, we've made it. I really hope that this talk has made it clear the benefits of using EM sensors, the flexibility of the system without ground contact, and the ability to operate in virtually any soil conditions or time of year using very low power makes it attractive. It's a more productive and efficient method to map the commonly changing variables such as texture, moisture, salinity, compaction. We just to name a few, we went through them all. This, along with also the ability to use EM to improve and generate better management zone maps, they help, ultimately will improve yield. And this is something that is going to be needed and improved for future demands posed by our increasing population. At the same time, it will help decrease the stress on soils by increasing the overall health and agriculture of the cultivated lands, which from your opening statement is essentially what you're there to do. Hopefully this, the knowledge base from everything that's provided by the tech team can help to get this. And I hope again that I did my small part, at least when it comes to EM, and covering as much as I could. So with that, I guess I leave you to questions.
That was great, Mike. Very informative. Speaking as someone who doesn't have a whole lot of experience with the technology, I certainly learned a lot. Do we have any questions out there? I've got a couple. So you showed in one of your earlier slides some sensors mounted to a helicopter, and I mean you've clearly made the case that you can how do you say you can learn about an area much quicker using an EM sensor than say going out there with an auger. Can you think of it? Is it too pie in the sky to think that there would be a way to kind of further enhance that by say mounting an EM sensor to like an aerial unit?
Yes, that's actually, so I probably should have at least included one slide on covering that, but I did not. And now that you bring it up, so that's great. You asked a really good question. We actually do have currently, we are involved with some pretty big drone manufacturers, well-known, that are using our metal detectors for the detection with our military applications, also for non-military, but a lot of it is being military, trying to detect unexploded ordnance or UXOs, metal detection. So we're familiar with that, and that's what first got us into that area with drones and using sensors flying around. As opposed to, I know you asked because you saw pictures historically on an airplane, but current use on drones, we started first with our metal detection, but we have had some inquiries about doing that with our EM devices for measuring soil conductivity. And it turns out we actually we do have a project, a research and development project going on where we're developing a super lightweight EM38 that can be flown by drone. So basically doesn't change anything about your survey. I mean, you need, as long as you have a drone that's capable of flying low to the ground, obviously the survey is conducted the same way. These are proximal sensors. It's not something you're going to fly. You're not flying a drone with a camera to take pictures from 100 meters in the air. You need to be fairly low height. But anyway, if you're doing that for other purposes, absolutely, we do have an R&D project where we have a prototype for an EM38 called an EM38 Lite, which can be flown by a drone, just as you just asked. So that was a good question.
That's interesting. And so does that, I guess.
Oh,
From the example that you showed with, without a helicopter or even a plane or something like that, is that using, you mentioned the time and was it the frequency domain? Or the
Frequency,
aerial?
it would be free. It would be frequency domain. Yeah, it would be no different. It's the same instrument as what you see here. These the EM38 on the sleds and towed here. I mean, it's the same instrument. It's this instrument, but just a light, I mean, this instrument doesn't weigh that much, but for drones, they want to go super light. So the standard instrument is something like five kilograms off the top of my head. We're trying to build something closer to 2 kilograms. So just cutting out some of the weight, making flight a little more efficient. So it's conducive to being flown by a drone already. So it wasn't a terribly difficult project. Anyway, I was going to mention the timing. We believe we'll have an instrument capable of running tests by later this fall, going into the winter. So it's not something out there in the future. It's here. It's like months away, basically.
Good to hear. See, a couple questions came in the chat. What are the performance of these things in urban environments where you have a lot of things that might be causing like background noise, such as overhead lines?
Yep. Well, if you're in an urban environment, whenever you're using an electromagnetic instrument, the rule of thumb is typically you need to be about a coil separation distance away from metal sources or fences or power lines and things. So walls, buildings. So let's say you're using the EM38, which you're looking at here, the coils are separated by about 3 feet, right? So as long as you're about 5 to 10 feet away from building walls or other pieces of metal, you're okay in terms of interference. But there's 2 kinds of interference for EM instruments, which of course I didn't really cover. It wasn't the scope of my talk, but you have to deal what all EM instruments are. Of course, they act as metal detectors as soon as you have a very, a piece of metal within range, right? And that's because it's concentrated. So the field's concentrated. You get basically the how I described how we calculate the soil conductivity. Well, that assumes a certain level of conductivity in the soil, but the electrical current when you have a piece of metal is off scale. So everything breaks down, and what you get is an anomaly in the data set or a spike, which is typical of a metal detector. So the same instrument you're using for archaeological purposes, or you're looking for soil salinity, changes in texture of the soil, moisture. If you pass over a pipeline, you're going to see the pipeline. So that becomes, if you're not looking for that in an urban environment, you're going to see that because it's designed to do that. But the other interfering property would be distant noise sources like a cell tower, other things emitting an electromagnetic field like a cell tower or a power line. And again, as long as you're further away than generally the length of the instrument, you tend to be in a safe zone. But yeah, those are the main concerns.
Okay. Oh, geez. I want to translate these people's questions. So someone was asking, what's the cost of an EM38?
The cost?
Yeah.
Am I allowed to answer that?
I guess we'll have to set some rules aside. Yeah.
That's all right. 20,000. The EM30. You're talking about 20,000 for the sensor. Pretty much everything you need, but there's obviously other options. But the sensor itself is about 20,000 US. Sorry.
There's a couple other questions in here that I don't really want to translate. Let's see. Snow cover. How would snow cover affect the performance for permafrost?
Sure. Yeah, good, great. Oh, good questions. I love it. So one of the earlier applications of EM induction systems was for permafrost mapping. But I'll answer it in 2 parts. So first of all, snow itself is resistive, right? Because it's just frozen water. So it's not going to do anything to the electromagnetic response. If you're doing a survey and there's snowpack, the electromagnetic field just passes through that. The only thing you see is the conductivity of the soil. So it doesn't matter. In some cases, we have people that want to operate over snow because it makes life easier for a few different reasons. The thing you have to take into consideration when doing surveys in frozen ground is the difference between if there's a change because of the snow, if there's pockets, if the snow is very deep, and the instrument is physically further away from what you're measuring, the absolute values may be different if you're comparing from when you did the survey without snow to when there is snow. So it has nothing really to do with the snow changing it's just the distance. If it's a pack of 3 feet of snow, you're further away from the soil. Yeah, but the only other thing to consider is when at the bottom of the snowpack, if it's a deep snowpack, let's say in different parts of the field for some reason, there's more, I don't know, methane coming from the ground, which is causing more melt. Some other reason it's melting. If you have some melting snow, it becomes electrolytic, which can produce a more conductive response. So it's actually possible to then be mapping which is why it's a good permafrost application, where it's still there and where it's kind of thawing out, because where it thaws out, you should start measuring increased soil conductivity. And just to throw a cool thing in there, we actually also have a case. Our instruments are used for in the high Arctic and Antarctic to measure ice thickness, because you have a perfect 2-layer case. The ocean water is fixed at some conductivity, and then the frozen ice is 0 conductivity. So the only thing changing is how thick the ice is, which changes how the distance of the sensor from the water. So you can actually, almost like mapping claypan, think about it that way. As the thickness of the clay is changing, the conductivity changes. Same thing with sea ice thickness. So anyway, thought I'd throw that in. Yeah.
Is it possible to determine the depth to a silica or carbon band at depth based upon the return current?
You're gonna have to ask that one more time, because it kind of, as you asked it, sounded like you're breaking up, and I just want to make sure I understood it.
Would it be possible to determine the depth to silica or carbonate at depth based upon the return current?
Well, okay, so again, you need to have a contrast in the matrix or the material. So if the carbonate layer, like we for different applications, our EM systems are used to find subsidence, any voids in the ground, like in the Florida. So looking for these pockets, but what you need is the contrast and conductivity. So specifically trying to detect, yes, but you need to have something that's, let's say, conductive above that. And then, yes, you could determine through some inversion, it is possible to determine what the depth would be, because there is a contrast and conductivity. If you're trying to determine this contrast and the two things have similar conductivities, they're both resistive, you can't do it. There's
Sure.
nothing for you, right? So yeah, that's how I would answer that.
The difference. Let's see. Any examples such as published papers on use for locating freshwater inputs into coastal pond soils?
So one more time, if I understood, read it one more time. Sorry.
Are there any published examples of using electromagnetic induction for locating freshwater inputs into coastal pond soils?
So freshwater, okay. So so I'm assuming that's coastal to ocean.
Yes.
So that's, yes. The answer is yes. There are actually. I can think of 2 studies in New Jersey. Salt. It was a marsh. Actually, and then there's also an example with a deeper going system where they're mapping the recharge of an aquifer into the St. Lawrence River, St. Lawrence Seaway, which is, of course, not freshwater, more brackish. And they were able to map the bottom of a section of the bottom of the river, showing, and this is a paper presented at the SAGIP conference, I can remember, and showing how the aquifer, the conductivity map shows where the pocket, there was missing conductivity, which is where the fresh water was recharging back into the river. So it just sounds similar to what I was just asked by this individual. So yeah, there's some, they can email me. I can forward the information. Absolutely.
Yeah. On your opening slide, did you have your email by any chance?
Oh, yeah, that might be a problem. Did I? I probably did not. That's I don't think I did, but I will give it to everyone right now. Yeah, I guess I didn't. Well, my email address is very simply my first name, Mike, M-I-K-E, at Geonics.com. Pretty easy to find me, actually.
And I want to express to everyone on the call that, talking with him, Mike, yesterday, that he's very receptive to answering, call it tech support questions. So feel free to reach out to him. Well, I think that gets us to the questions, and we're just about at the top of the hour. So I will close it by thanking you for presenting this to us. It was wonderful information, and since it's recorded, I will post it. And other than that, again, thanks for attending, and hope to see you guys at the next one.
You're very welcome, and yeah, anytime. If you need me to give another talk, let me know.
All right.
As long as it's on EM, of course. Got to be on EM.
Gotcha.
All right.
All right. Bye-bye, everyone.
Okay. Goodbye. Thanks.